All right, number 21. Which of the following can affect the value of a correlation coefficient R? Change in measurement units, not necessarily. Change in which variable is called X and Y. That would impact slope and y-intercept. It'd be your least squares regression line, LSRL, but it wouldn't change the correlation. Correlation is how the variables relate to one another. So it's definitely not D because I already eliminated one of them. Adding the same constant to all values of the X variable, that's just going to shift everything over to the right. That's not going to affect the correlation. I'm just trying to visualize, just making sure. So if I have, let's say, this set of values here, and I pick them up and shift them over to the right, the strength of the relationship between these values is not going to change. All right, so it's going to be the same here as it is here. The line that fits the data will be different, but that won't affect the correlation. Change in measurement units, just thinking back to that. Oh, I already discussed that one. If I did a Fahrenheit to Celsius over time, the relationship that exists, I mean, hot will still be hot. It's just a question of whether you're calling it 100 degrees or 200, what is it, 212, 216, something like that, if it's Fahrenheit, 0 versus 32. But it's still going to have the same relationship. So that would not necessarily be true. So, yeah, none of the above seem to affect that strength of the relationship. AMA wants to determine the percentage of obstetricians who are considering leaving the profession because of rapidly increasing number of lawsuits against obstetricians. How large a sample should be taken to find the answer to within plus or minus 3% at the 95% level. All right, so it looks like, well, they didn't give us. Yeah, so we're just looking for sample size calculation. So again, back to the formula sheet. Let me pull it up. I keep losing track of where I put it. So one with the little acorn for a college board. So what we use is the standard error calculation. Right? Margin of error. Right? So there is a formula that you could memorize. Some people prefer to do that. I'm not one of them. Right? So I know that if I were to do, and they didn't say anything about determine the percentage of obstetricians who are considering. So it's population proportion. All right. So in our population, is it a population proportion? Let me see. Percentage of. So we need to do a margin of error for a population proportion because they are asking about the percentage, right? So if we knew more information about number of trials and things like that, then it'd be a different story. Then maybe we could use a population mean. Population mean. So the confidence interval formula, even though they're not asking for a confidence interval, I'll just kind of show you where the margin of error formula comes from. P hat plus or minus Z. I use alpha over 2. Everybody else seems to use Z star. All right. So you might see that Z alpha over 2, same as Z star, or at least in this context. Times the square root of P times 1 minus P over N. All right, this part here is your margin of error. All right, so that whole thing really just kind of boils down to P hat plus or minus 0.03. All right. So we're equating these two to one another. So these two are equivalent. So I would do 0.03 is going to be equal to Z sub the 95% confidence corresponds to an alpha of 0.05. So an alpha over 2 would be 0.025 times the square root of P times 1 minus P over N. And for this kind of question, we do have to make an assumption. There's really no way around it, right? And that would be that it's a 50-50, right? Whether or not they're leaving the profession. It's an assumption that we have to make. So assume P is equal to 0.5. So I have 0.03 is equal to the Z sub alpha over 2, which I can get from my calculator. Probability, distributions, normal, inverse norm. When you're given a percentage, you use inverse norm to return the particular value, in this case a Z-score. I'll drop the negative and just go with the 1.96. Because these numbers are so far away from one another that a little bit of rounding isn't going to be a big deal. So times the square root of 0.5 times 1 minus 0.5, so another 0.5 over N, right? And so we then solve for N. That's the whole idea here. So I'll show out some of the steps here. I'm going to kind of jump to the calculator a little bit, but I can take the 1.96 and divide it out of both sides. So 0.03 over 1.96 is equal to the square root of 0.25 over N. All right, the square root of 0.25 is 0.5, so I can do that too. So 0.03 over 1.96 is equal to 0.5 over the square root of N, using proportion magic from Algebra 1 and geometry. Cross multiply, cross group if you want. This would be equivalent to 0.5 times 1.96 over 0.03. And then you would go ahead and square both sides once you get there. So I'm going to do it. 0.5 times 1.96 divided by 0.03. You take that number and square it. And you get something like 1067. The closest one is choice E. All right. Yeah, so that takes care of that. The answer key in the Barron's book, it gave the right answer, but it gave a calculation that didn't make any kind of sense. All right, so in case you were wondering. For number 23, suppose you did 10 independent tests of the form, so hypothesis tests versus, so null of mu is equal to 25 and alternative mu is less than 25. What's the probability of committing a type 1 error and incorrectly rejecting a true null hypothesis? All right, so they were kind of, I'd say, nice here, and maybe this will help with other problems. So, the old suggestion whenever you're taking a test, make sure you read all the questions, because sometimes one question will help you figure out another. So here, they're telling you that a type 1 error is incorrectly rejecting a true null hypothesis. So that's kind of nice. Like if you forgot what the type 1 error is, then that'll help you get past that. All right, so now in this case, so aside from that piece of information, they're saying what's the probability with getting a type 1 error with at least one of the 10 tests. All right, so probability at least one type 1 error. Now we have a formula for that. Probability of at least one is equal to 1 minus the probability of none. All right. So this is saying find the probability of getting no type 1 errors in the 10 tests. All right. So the probability of getting a type 1 error is also alpha. All right. It's the maximum accepted value for alpha, as in a rejection area, a comparison to a p-value. All right. So this is what we allow, no more than 5%. And that's kind of just a number that was sort of decided upon. It's related to the normal curve, but it just kind of feels, without getting into more calculus origins of this, it feels like it comes out of nowhere. But the probability of not a type 1 error, I'll go T1 error. A single time, it would be 0.95. But because it's happening 10 times, and we're assuming the events, well, we're not assuming it, they tell us that they're independent tests, 1 minus 0.95 to the 10th power we're looking at something in the neighborhood of 0.4. So about 0.4, which would be choice B. All right. So what was shaping up to be kind of like a hypothesis test, confidence interval type scenario, it really kind of morphed into a probability question. But it's kind of a mixture of the two ideas, because if you don't know that the type 1 error is, the probability of that is your alpha value, then, it's kind of problematic, we'll put it that way. Which set has the smallest standard deviation? Right? They give you raw data, which isn't a bad thing, because worst case scenario, you can just type in the information. Right? So your NumWorks calculator will do that for you. When we're talking about standard deviation, though, we are talking about data that's or how spread out data is. So you have a data set that's more tightly grouped versus one that's more spread out. So you can reason your way through it. But while we're here, might as well. The number sets or data sets aren't too lengthy, so I don't even need shortcuts to type it in. So in my value V1, numbers 1 through 7, and value V2, if I want to make it a frequency table, I could, but I don't want to, so I'm not gonna. And then 1, 4, 4, how many 4s? 5 4s? 3, 4, 5, 7. There's more brute force, but if you go to stats, doesn't say it's population or sample, so I'll be mindful of that. All right, so the smallest one appears to be the third one. This is less spread out. So they wanted the smallest standard deviation, so the one that starts off with Roman numeral 3. All right, and then the one with the largest standard deviation, that would be largest one looks like it's the second one. All right, so yeah, that's pretty spread out. Not much more spread out than in the case of Roman numeral 1, but because you have a bunch of values on the high side and low side, that does support that. So it's going to be choice E. Oops, sorry, didn't mean to hop ahead. Number 25, I'll start reading it. Researcher plans to study to examine long-term confidence in the U.S. economy among the adult population. She obtains a simple random sample of 30 adults as they leave a Wall Street office building one weekday afternoon. All but 2 of the adults agree to participate in the survey. Which of the following conclusions would be correct? Sounds like, before getting into the choices, it's fairly poorly designed, right? Like a convenience sample type. But we'll see. A proper use of chance. Did that happen? She obtains a simple random sample of 30 adults as they leave Wall Street building one weekday afternoon. I mean, proper use? It's a use of chance. Well, I'm not going to get into like how she decided on the 30, but we'll see. All but 2 of them agreed to participate in the survey. High response rate makes this a well-designed survey. Response has nothing to do with the design. It's a consequence of the design, right? The ends justify the means. She may have lucked out and came up with a good response set, but that doesn't mean it was a well-designed survey. Selection bias makes this a poorly designed survey. There is an element of that in there. We'll see. Voluntary response. Well, she randomly selected them. Now, whether or not they choose to participate, that's the gray area for a voluntary response. When we think about voluntary response, we're saying that the individuals are going out of their way to be part of the survey. They weren't selected. So that's not the case. Lack of anonymity makes this a poorly designed survey. I don't know. This doesn't seem to be like a hot button topic necessarily. Long-term confidence in the U.S. economy. It doesn't mean it's a poorly designed survey. Let's just put it that way. I don't think knowing the person's name or anything like that would impact how they responded. Right. Now, something about like how the interviewer asked the question, that might have something to do with it, but that doesn't seem to be indicated here. Proper use of chance as evidenced by simple random sample makes this just going back to that idea, it doesn't mean it's a well-designed survey. Like the parameters of the survey where she's standing outside of a building. Why that building? What's the purpose? I think it said building. Wall Street office building. Why that particular building? Why that time of day? What are the factors that impact any kind of variables that go in? So it doesn't mean that it's a well-designed survey. So the only one I'm left with is C. If there is selection bias in it, then that is the result of a poorly designed survey because it opens the door for that sort of thing, right? So, yeah, that seems to be the one that makes the most sense. 26. Which among the following would result in the narrowest confidence interval? Right. So, small sample size and 95%. Well, focusing on the confidence levels, we know that the larger the confidence level is, the wider the interval. Right. So you could just kind of really just sort of eliminate the ones with the larger confidence levels, right? Because those are going to be the widest. Now, which one is going to be wider between the large sample size and the smaller sample size, that's a different conversation. But in a comparison, all things being equal, between 95 and 99, the narrower one would not be associated with the 99. Now, a large sample as opposed to a small sample, all right? So when we come up with I'll just use the testing claim about a mean. Let's say I have, I'll just use T. T alpha over 2 times S over the square root of N. So N references the sample size. If N increases, then S over the square root of N would decrease, right? So you can think about it in terms of limits, or just simple computation. If you divide by a larger number, you're going to get a smaller result, all right? And this is our standard error. If the standard error is smaller, then the margin of error is going to be smaller. All right. The plus minus part of the confidence interval is what dictates how wide the interval is. So if your standard error decreases, right? Yeah. Oh, sorry, I just had a moment there. The margin of error, so ME, or just E or just M. So if your standard error decreases, so gets smaller and smaller and smaller, then your margin of error is also going to decrease. And the interval width, which is your plus minus part of it, will also decrease, making the interval narrower, right? And that's in the case where you have a larger sample size. So between small sample size and large sample size, if I want to have a narrower interval, I'm going to want the one that's got the lower confidence level and also a larger sample size. And that's really just knowledge of the formulas. And again, you go to the reference sheet. Those formulas are there. You just got to make use of them. All right. For number 27, consider the following scatter plots. Let's see. This is strong negative. This is 0. And this is, I would venture to say, perfect negative. All right, so I'll just make up numbers. All right, so this is the plot 1, 2, and 3. Those stray marks are really getting at me. All right, the R value here would be a -1. For no correlation, R value is 0. Horizontal line corresponds with a 0 slope. Since slope and correlation are proportional, if the slope is 0, then your correlation is going to be 0. All right, strong negative, I'll just make up a value like -0.75. Doesn't really matter. But in order of least to greatest, I'll give a little subscripts here. This is 1, 2, and 3. All right, so the smallest one would be my R3. Next up would be my R1. And then after that would be my R2. So it looks like choice D. Uh, 28. 2 games involving flipping a coin. In the first game, you win a prize if you can throw between 45 and 55% of the coin outcomes being heads. In the second game, if you win if you can throw more than 80% heads. For each game, would you rather flip the coin 30 times or 300 times? Fair coins? I'm assuming. They don't say it one way or the other. So if I increase the number of trials, I'm going to get closer and closer to the true probability. This is going to be law of large numbers. Increase number of trials. You get closer and closer to the true probability. It also means that you're reducing variability. All right. It's not going to be even remotely grammatically correct, but get closer to true probability. All right. I kind of look at it like the Giants beat the Patriots in the Super Bowl. They beat them twice. It was great. I was at one of them. It was one of the highlights of my adult life. But I am realistic in saying that if the Giants played the Patriots 10 times, they probably still would only win the 2 times. All right? Because one team was, at least on paper, a better team, just not on those days. If I flip a coin 5 times, it's a lot more possible or probable that I would get all 5 of them would be heads than it would be if I flipped a coin 1,000 times and expected all 1,000 of them to be heads. It's gonna regress to the middle. So if I did it 300 times, that I'm going to get something closer to this interval than I would get to this interval, or I mean, more than 80%. Right. So for each game, for the first game, I would want to do it as if I'm playing that first game, I'll win the prize. I want to have as many attempts as I can get. Right. And for the other one, I want to have as few attempts. Right. Because it's going to regress to the mean. So I want 300 for the first game, and I only want I like 30, I guess, but I'll take like something even smaller, like 10, 5, something like that, as low as I can get. All right. So choice would be D. And again, the stray mark is really becoming a problem. City planners, they're trying to decide among various parking plan options ranging from on-street in comparison to multi-level and all that stuff. All right. The merchants claim that the shoppers park for an average of only 47 minutes in the downtown area. The planners have decided to tabulate parking durations for 225 shoppers and reject the merchant's claim if the sample mean exceeds 50 minutes. Right. If the merchant's claim is wrong, right, so I'll make a little note here, merchant's claim is that mu is equal to 47. If they're wrong, if the merchant's claim is wrong and the true mean is 51 minutes, so we're saying this is wrong, the mu is actually 51 minutes, what is the probability that the random sample will lead to mistaken failure to reject the merchant's claim? And then they give us a standard deviation. All right. So they're telling us that the true mean is 51. What I'm looking for is this little component here, how that fits into everything. Sample mean exceeds 50. So we're kind of treating that as our sample mean. All right. We'll reject the claim if that sample mean is more than 50. Right. As opposed to a mistaken failure to reject the merchant's claim. Right. So a mistaken failure to reject would be, so we're essentially looking for the probability that the sample mean is not going to be more than 50, even though we get a mean that's 51, or this is a true mean. All right, so we're looking for the probability that the mean is less than or equal to 50. So just some mean is less than or equal to 50. We're assuming a normal distribution. All right. We get that from the large sample size. I didn't write it, but n is equal to 225. All right, it's large enough. So we're good there. So if I want to find this probability, I'm looking for any z-score. If I convert this over to z-scores, it would be, I'll worry about that in a minute. The fraction is going to be 50 minus the true mean of 51, standard deviation 27 over the square root of 225. I'm looking for that's the z-score corresponding with x. So I'm looking for the instance where z is less than or equal to that. And that would be our probability. I don't see one with a less than or equal to symbol, but because this is a continuous distribution, we don't actually distinguish between the boundaries. So this is really the same as choice C, I think. Yeah. All right, that's probably one of the trickier ones, just because it's really kind of a tough question to kind of figure out what it is they're asking you to do at first. Right? And really that 47 doesn't really play much of a role. It's the idea where I underlined it, the merchant's claim is wrong and the true mean is 51, so that establishes this. And the other part, where was it? If the sample mean exceeds 50, it's a question of being wrong and the whole double negative aspect of it. So it's kind of a spicy one. Number 30. Let's see if there's a question that's a little nicer to us. Consider following parallel box plots indicating the starting salaries in thousands of dollars for blue-collar, white-collar workers at a particular production plant. What's the correct conclusion? Well, let's take a look. The first one talks about ranges. Let's see. Maybe if I just kind of ballpark it. Range, again, is max minus min. So if I ballpark this, probably looking... Sorry, I just got a little out of whack here. Something in the neighborhood of maybe 10. I'm assuming. Maybe 27-ish. All right, so let's say this is like, I'll say 27 minus 10 is 17. And this one, man, we're really kind of eyeballing it here. They didn't give us any other information, right? So this is like 42, and maybe let's say 57 minus 42. Well, that's going to be 15. Well, I wouldn't say the ranges are the same, but I just guess, so I don't know that I can say that they're not the same. The mean is equal to the median. So in each distribution, the mean is equal to the median. It is symmetrical in both cases. Each distribution is symmetric. That's also true. Each distribution is roughly normal. Distributions are outliers of each other. I'm guessing that there's a typo here. I believe this one should say, which of the following is not a correct conclusion? Because in a symmetric distribution, the mean and the median should be roughly the same. These are two symmetric distributions. They are roughly normal based off of just the way a normal distribution looks in a box plot. And the low bound of this graph is way outside 1.5 the IQR. So here's my IQR. Oh, lovely. All right, so if I want 1.5 of those beyond, so here's one. Well, maybe it's not way outside, but it's definitely, or it appears to be outside. Could be close. So this would be, oops, half again. All right, so not all of the graph is outside 1.5, the IQR, but the other way around it certainly is. All right, so I could show that real quick. This is my IQR. Let me try it a different way here. So that's one IQR below the lower quartile, and that would be another half an IQR. So it's really not so much that they're outliers of each other. It's just that the lower data set is an outlier from or of the upper data set. But the one thing I'm not really able to say for certain is that the ranges are the same. So I'm going to go with choice A here and assume that this is a typo. All right.